All right, next I'd like to go through a few more details regarding the structure of the Earth's atmosphere. And we'll need to start with some basic concepts that relate to how we measure the atmosphere. One way is by means of the density. So we can think of density as being mass per unit volume. And so there's a certain concentration then of atoms in the atmosphere that exist in a certain volume. So we can think of that in terms of the density. And so the density then tends to get larger near the Earth's surface. And it drops off rapidly with elevation above the surface. And so our rockets that are put into orbit don't want to feel atmospheric drag, and so they want to be above pretty much the entire atmosphere. So it's considered safe to put a rocket at 200-mile orbital distance from the surface. So we can say that the atmosphere extends to something like 150 to 200 miles. Now, it does vary a little bit depending not only on the seasons, which heat up the northern and southern hemispheres differently because of the tilt of the Earth's rotational axis, but also because of the output of energy from the sun. The sun goes through different kinds of cycles called sunspot cycles. And when you're in a higher density of sunspots on the sun's surface, it turns out that the sun produces more radiation, actually heats the Earth's atmosphere up. That atmosphere can rise up to a greater height. And so there's a little bit of a fluctuation in the upper atmosphere, but it's considered pretty safe to put a spacecraft up at 200 miles above the Earth's surface and not expect there to be very much atmospheric drag. Okay, and so the reason why the density is greater near the Earth's surface is due to the fact that there's more weight pushing down on the near surface atmosphere due to the weight of the upper atmosphere. This is due to gravity. So there's just more weight pushing down on the lower atmosphere because of the existence of the upper atmosphere's weight, and that adds to this kind of crunching effect. Now, I have to wave my arms a lot if I don't use the concept of pressure here. So let's also talk about pressure. We can think of pressure as being force divided by area. And so the force in this case could be considered to be essentially the weight of the atmosphere on a given area of the surface. And so the pressure of the atmosphere then typically can be measured in terms of taking a square inch of surface area of the Earth, 1 inch by 1 inch, by about 200 miles up, maximum height of the atmosphere, and weighing that. So if we weigh that square inch of atmosphere what we end up with is a counterweight on this side, which would be 14.7 pounds. And so we say then that P atmosphere, pressure for the atmosphere, is 14.7 pounds per square inch. And that measures the pressure of the atmosphere due to the weight of all of the rest of the atmosphere pushing down on that surface on each square inch. So this is considered to be our normal pressure. But there are variations in this pressure that can be due to the unequal heating of the Earth from the sun. Now, why would this happen? Why would the sun not heat up the Earth equally? Well, the reasons for this are actually many. One is that the sun is in a different position in the sky with each season. As we saw before, higher in the sky during the summer months, lower in the sky during the winter months. And also the length of the day varies. We also have the sun is in a different position in the sky at different times in the same day, regardless of the season. So if the sun were directly overhead, which it won't quite get to in our latitude, but if we're coming straight down, then you'd have the most direct heating there. And so that's why near the equator, you tend to get hotter temperatures. But if the sun's rays are coming in at a sharper angle like this, either later in the day or in more extreme parts of the seasons, you have less heating. This is why during the winter time, when the sun is lower in the sky, you tend to need less sunscreen in order to prevent a sunburn. Whereas when the sun's rays are more direct, which is more typical of the summertime, you would need more sunscreen. And so the different parts of the Earth's surface then are being heated differently at different times of the year on an average day, but are also being heated differently throughout the day as the sun goes from higher up in the sky to lower in the sky from day to night. Another reason for the unequal heating is that water absorbs sunlight better than land does. So the water tends to absorb something like 90% of the solar radiation. The land is quite variable because the land can be different colors. And ice tends to reflect sunlight and absorbs very little. And so this is really not only the source of variations in atmospheric pressure, but because of that, this is the source of our climate and weather. Because if all of the pressures and all of the temperatures were the same worldwide, we wouldn't have any weather, excuse me, or climate. Okay, so with these ideas in mind then, let's just talk a little more about the idea of pressure. In the ocean, the pressure increases with depth. Such that you get a 1 atmosphere's pressure increase. Remember, that was 14.7 pounds per square inch for every 33 feet or 10 meters of depth. So in other words, if you're at 33 feet depth, you're feeling not just the pressure due to the weight of the atmosphere, but also due to the weight of the water, all the way down to 33 feet. If you go down to 100 feet, then that's going to be 3 times 33 about, and so that's 3 atmospheres, plus the atmospheric pressure of the air is 4 atmospheres. So you have 4 times the pressure pushing down on you at 100 feet beneath the Earth's oceans as you would at the surface. So there's a tremendous amount of variation of pressure with depth. There's a smaller variation, though, in the atmosphere. And this drives the winds. This is the source of the wind. We can consider wind to be a convection current that is driven by the mass motion, heat moving from high pressure to low pressure. Okay, so let me try to explain this a little bit. We have this smaller variation, so it's not nearly as extreme as what we find when we go beneath the surface of the oceans. But you could still get a variation in pressure on the order of a few percent of atmospheric pressure, either above or below. And so let's say you have a region of high pressure. Now, by a region of high pressure here, I'm not talking about 4 atmospheres pressure beneath the surface. What I'm talking about instead is just a few percent above 14.7. Which is our normal atmospheric pressure at the surface of the Earth. So this is the case then, and over here we have low pressure. Which would be, say, a few percent below 14.7. Then the natural tendency is going to be for our convection currents to deliver energy from high pressure to low pressure. So in high pressure, and this isn't always the case, but let's say that it's the case here. This is due to more energy in higher temperature. And let's say that this is a lower temperature air mass. As well as higher pressure, we could say that oftentimes, not always, but oftentimes the temperature is also higher in the air mass. So we could think then of this energy as wanting to go from higher to lower pressure. And so why is that? Well, you can think in terms of pressure as being kind of a battle between the molecules. So if the molecules are exerting equal pressure on each other, this one knocks that one back, but an equal amount of the time, this one knocks that one back, and so they don't really go anywhere. But what if the one that has more pressure is getting in more hits than the one that has lower pressure? So it's a statistical thing, because you have a lot of molecules doing this, but if the high pressure air is getting more hits on the lower pressure, then the average motion is from high to low. And so that's essentially what's happening here, is that we've got the motion of the air from high to low, because the high pressure air is pushing harder this way on any given area than the low pressure air is pushing that way. So we have 3, say 2, 3, 2, 3, and so the air tends to move naturally then from high pressure to low pressure. And so normally then in a high pressure region, if there aren't any other influences, we can draw the flow of the air as being away from high. If everything else is lower pressure around it, and if we're dealing with a low pressure air mass, we can say that the air, if everything else is equal, is going to tend to flow inward toward a low, like that. Okay, but that is without any other external influences acting. Turns out that there are other things that affect the flow of air around a high or a low pressure air mass. And these have to do with what are called Coriolis forces due to the rotation of the Earth, as well as differences in temperature between the equator and the poles. So the flow of air out of a high pressure region we know that it's going out because high pressure tends to push harder this way than the low pressure will push back. But the flow of air is also influenced by A, the difference in temperature between the equator and the poles. And 2, or B, the rotation of the Earth. So both, and these are associated with what are called Coriolis forces. Which you don't need to be an expert on for this class, but just wanted, if you want to Google this and get more information on it, that's what it's called. And so if we have, say, a high pressure air mass in the northern hemisphere, here's the Earth, here's the equator, here's our high pressure air mass, let's say. The general tendency of the air is going to be to want to flow from the equator to the poles, either in the northern hemisphere or the southern hemisphere. But this is only if the Earth isn't rotating. When you add in rotation, the flow of the air starts to look like this. This way. And that way. There we go. Okay, so now we've got it right. This is a combination then of both the difference in temperature between the northern and the southern, between the equator and the poles, and the rotation of the Earth in the northern hemisphere. Okay, so why is this the case? Well, air that is coming out this way, as it rises up, it starts moving, the air is moving faster at the equator to go all the way around the Earth in one day. So as it gets closer and closer to the poles, it's running into air that is going slower. And so the natural tendency then of that air that's coming from a lower elevation as it moves up is to get ahead of the air molecules that are moving more slowly at that greater latitude. At this point, the air has come up to this point and is cooled off and is starting to return to this point. And so the flow of this air is going to tend to curve back down toward the equator. That air that comes out this way is going to tend to be deflected toward the north because warmer air is going to want to move toward cooler air. And so it's a little more complicated than this, but the result of all of this is a convection loop. And this convection loop is just the flow of air around the high pressure region. And it tends to be clockwise in the northern hemisphere. But because the southern hemisphere has essentially everything going in reverse, it will tend to be counterclockwise in the southern hemisphere. So if you were trying to model these convection loops, you would have a number of different mathematical equations which would be working together, which would include things like temperature variations, the rotation of the Earth, and also differences in density of the air. So all of those things together will give rise to a more coherent mathematical description of these kinds of circulation patterns. But what this is associated with is what we call an anticyclone. And tends to be less severe in terms of the wind conditions that are produced than a cyclone. So what's a cyclone? Well, a cyclone is just the airflow around, instead of these being high pressure regions, we could look at the airflow around low pressure regions. Here's the equator. Here's our low pressure. And so basically what we'll do is we'll just take the same streamline of air, but we'll change the direction. So the air tends to move in toward a low rather than away from a high. So the same curvature here of the airflow, that's maintained, that the direction of the wind is going toward the low instead of away from the high. So it tends to go like this, but what this is giving us is a counterclockwise circulation around the low. So this low pressure region might just be the result of the air being cooler because of unequal heating of the Earth's surface. And so this then tends to be what we call a cyclone, which gives rise to much more intense winds. And this is the counterclockwise circulation in the northern hemisphere. But the reverse is happening in the southern hemisphere. So we would have to reverse these airflows here. And so this would give rise to a clockwise circulation in the southern hemisphere.